Then, okay, so we are going to have another lecture today on non-thermal technology in food processing. Okay, so we have talked about novel thermal technologies, and today we are talking about non-thermal technologies. So non-thermal technologies have been seen as an alternative treatment for food processing, which is gentler in comparison to the conventional thermal method. So it has reported to have very minimal or no effect of non-thermal technologies towards the food nutritional quality and the characteristics of it, the flavor, sometimes even the colors not changing. Okay. However, due to the uniqueness of food type, materials, and product, only a certain non-thermal technology can be applied to food with the aim to inactivate pertinent microorganisms, naturally occurring enzyme, and an optimized process with a minimal effect towards the quality of the food with minimal cost and energy usage. Okay, what am I trying to say is that for each of the non-thermal technology, there's going to be a very specific food that they can treat with effectiveness. Okay, so a certain technology are not suitable for a certain type of food product. Which food product we are going to be discussing next. So we have gone through omic heating last week. We have also gone through the radio frequency and infrared heating last week. Okay, for this week, there's going to be about 7 non-thermal technologies that we'll be discussing. I have about 150 slides, but I hope I can go a bit faster. Okay, so we'll be discussing on the HPP, the pulse electric field, the ultrasound, irradiation, ultraviolet, and of course pulse light, cold plasma, and ozone. Okay, and if you could take a look at, although I've written here nano cavitation, I will not be going through the nano cavitation for today. Okay, but you can read further on about nano cavitation, which is relatively a very new technology that is undergoing a lot of research at the moment. It's basically using a very high shear pressure, okay, to kill off any microbials inside the food. So needless to say, it is very, very effective in treating fruit juice or liquid food in comparison treating to solid food, right? So if you look at the overview strategies, you basically need to understand the mechanism of it and the principles of action associated with the non-thermal food processing. So basically, we need to identify what are we dealing with. When we're talking about HPP, we are dealing with pressure. When talking about pulse electric field, we are dealing with electromagnetic field and so on. Okay, and the next thing that you guys need to know when dealing with food preservation with non-thermal technology is the merit associated with the selected non-thermal food processors. Okay, merit in terms of the parameters, the critical parameters, and also you need to look at the food composition of it. And also you need to understand the restriction associated with the selected non-thermal food processors. Only certain types of food processors are eligible for non-thermal preservation methods. Some are not so suitable, but you can still use it to a certain extent. Okay, so future processing trend is that previously we have what we call the traditional technologies, where we usually use a reverse engineering plan or method, where we improve on the design and also the control by redesigning the technology that we have. It's because to improve manufacturing performance, and obviously you want to improve the product quality, and hence you will be you will produce traditional food, what we call as a traditional food. But with novel technology, basically when you are dealing with novel processes, there are transformation, and of course there are preservation to a certain extent of the nutritional qualities of your food product. And from there, you can also improve the quality product, and sometimes, and hence why we call them novel foods, because to a certain extent, we improve the nutritional qualities of your food product, sometimes you can even produce what we call a functional food. Okay. So if you look at the future processing trend, the percentage of respondents indicating technologies with potential for commercialization in the next 5 years. Okay, so these are the data that was taken from a survey done by Kuchma in 2015, and obviously we have moved to 2023. So we are fast ahead of this. But looking at the future processing trend, the consumer is have very high hope that HPP, UV light, microwave heating would be the frontier of our technologies in food processing. Even if you look at the ozone, infrared heating, the ohmic heating, these are the frontier where they have really high hopes that this product would be developed into a market to produce to domestic usage, okay, instead of just in industrial usage. So basically, going back to the key drivers of novel technologies is why, because the consumer wants freshness, convenience, and less preserved food. And we also like to have enhanced safety and extended shelf life. And of course, sometimes we are dealing with very sensitive food products such as vitamin C. And when we treat them with very high heat, usually it would degrade. So we would like to retain as much as possible, especially talking about vitamin C and those vitamins that are very sensitive towards heat treatment. And of course, you also would like to have technologies that are lower in carbon footprints and to reduce the water consumption in order to have a greener technology, and of course, to engineer new food development, such as functional food, in order to deliver healthier food. Okay, other key drivers of novel technology are the major quality loss that was reported when you treat your food product with heat treatment, such as talking about off flavor or maybe sometimes color changing, browning effect, the color loss, the flavor loss, so a rancidity and a lot of other quality loss that we are dealing with previously. Okay, so non-thermal technology is basically a processing. We can consider having a very low temperature range, okay, lower than 40 degrees C. It would have a very minimal effect on the texture, aroma, and flavor, and of course, offering value-added products, new market opportunities, and added safety margins. Okay, so non-thermal technology also preserves processed food and ingredients during transportation and retailing and consuming food. And it provides safety attributes that is higher than the raw product. And you can also maintain the health and quality attributes that is equivalent to the raw product and enhance functional properties, and of course, providing broader, sustainable and environmentally friendly benefits. So what are the understandings? Okay, previously, take a look at the traditional food processing is basically putting ingredients together and then processing them, and then you would eventually come up with a product. But when we have novel technology, we have to study on a lot of things. Firstly, you need to look at the prototype design, okay? And then you, of course, need to analyze on the hazards, okay? Especially on the safety, microorganisms. And then afterwards, you need to validate in terms of the quality, nutritional properties, and so on. And then, of course, you would need to have regulatory acceptance. Here in Malaysia, aside from irradiation, all the other non-thermal technologies are not regulated yet by the health minister. And in fact, I think 60 to 70% of the food manufacturer in Malaysia are dominated by the small and medium enterprise. So normally, this enterprise do not use non-thermal treatment because to them, with the lack of expertise and the lack of knowledge about the non-thermal technology, so it has become a bit of a hindrance for them to adopt the technology in their food processing. So needless to say, When it comes to food processing, we are very much in the traditional sector here in Malaysia. I don't know on the Indonesian part, and maybe you guys can discuss further next week, in the next 2 weeks when we have class presentation. Okay. So another thing, another benchmark that we can evaluate or assess your novel thermal treatment, novel non-thermal treatment that is ready for industrial usage is you can measure through the technology readiness level. Okay, so we have the 1 until 9. So depending on which part, so basically if you were still studying on the fundamental part, we are only at the TRL1. Usually in Malaysia, for commercialization, we need to at least to the TRL3. And from there on, you can move on towards commercialization and industrial scale and so on. Okay, so recognition of novel processes, in fact, in US, United States of America, is a bit harder for them, okay, to recognize or even to give the consumer or even USFDA the confidence of novel non-thermal treatment. Okay, even in Malaysia, still the consumer is very much, the awareness of the consumer is very much still low. And I don't think that they are ready to accept the non-thermal technology yet. Except when we're talking about at the rural, at the urban area, maybe at the city area, they are much more acceptable towards it. But we're talking about newer technology to the rural area, to the kampung or to the village, and maybe it's not very much acceptable yet. Okay. But even in the United States, it took some time for them to accept this new technology. When you look at this, 2009, only then it was accepted that UVC to be one of the non-thermal technologies to preserve food. And even HPP was only approved in 2004. And 2008, irradiation for fresh iceberg lettuce and fresh spinach was approved. So although the technology has been there for quite some time, for them to be readily accepted and to be to make the technology to be a part of their food processing, it would take some time. Okay, and in 2010, USFDA first time approved a novel sterilization processing using a 915 microhertz microwave energy, which is what we call MAT, microwave assisted thermal sterilization for producing prepackaged food that is room temperature stable and can be kept up to 12 months. Okay, so the first subtopic of the day is the HPP. So what is HPP essentially? It's basically technology by which a product can be treated with a very, very high pressure. Okay, so it was first researched by Hyde in 1899 to preserve milk. And then it was only then commercialized in Japan in 1990 to treat acid food such as jams and for chill storage. And in 1991, they processed yogurt, fruit jellies, salad dressing, food sauces, okay, but also was done in Japanese companies. And it was then marketed in Europe and United States and Australia in 2001. So what is HPP? It's actually a non-thermal treatment of food by application of very high pressure, which is between 3,000 to 8,000 atmospheric pressure. Okay, so it is independent of the food size and of course the geometry of it, and their effect is very uniform and instantaneous. So it's basically using what we call an isostatic or a uniform pressure. Okay, so the process temperature can be specified as low as 0 degrees C and maybe sometimes as high to 100 degrees C. And the exposure time is a millisecond or to about 20 minutes, depending on the size of your product. So how much pressure? Okay, so when you look at the pressure exerted at the highest altitude and the deepest part of the ocean are considered as high pressure. Okay, so but for food processing, 200 to 800 megapascal pressure is required. 200 and 800 is somewhere around here, between 2 to here. Okay, so about 2,000 or 2.5 kilometers worth of deep sea until about 8.8 kilometers. So for inactivating milk enzyme, which is the alkaline phosphatase or protease, about 1,000 megapascal is needed. That is a lot. Is a lot of pressure. Okay. Usually 600 megapascal is the optimum pressure for processing commercial food products. So it is based on two principles. One is what we call the Le Chatelier, and another one is the isostatic principle. Okay, so the isostatic principle is basically telling you that the food products are compressed by uniform pressure from every direction and then return to their original shape when the pressure is released. Okay, so the products are compressed independently of the product size and the geometry because the transmission of the pressure to the core is not mass or time dependent, thus the process is minimized. And if the product contains sufficient moisture, pressure will not damage the product at the macroscopic level as long as the pressure is applied uniformly in all directions. So this is basically the process description of HPP, where you would put your product here. Okay, it is being put into a basket, and then it will be loaded into a HPP chamber, where a water will be pumped. The water will be used as the medium, okay, into this HPP chamber to help apply isostatic pressure. And from there, the product will be held at an isostatic pressure up to 87,000 psi to inactivate microorganisms. And then after certain holding time, to make sure all the pressure is lowered to a safety level, and then it will come out of the vessel and ready to be refrigerated until consumed. So the key benefits are basically, of course, you can enhance the food safety, and from there you can extend the shelf life, enable clean labels, so meaning food without preservatives, without colorings and acids, okay, and it can also reduce food waste and maintains the taste, texture, and nutritional value, and of course protect the brand reputation. And there's a link here if you want to look at the process closer. Okay. So there are two types of HPP. One is what we call the direct compression, where you would have the pistons here and you would have the pressure vessels. And of course, you can put your food product inside, and basically you would have a low pressure pump connecting to the pistons, and you can basically compress your product until to a certain pressure that you need it. Okay, another way of doing it is what we call an indirect compression. So the current industrialized HPP are using this type. Basically, you would have your pressure tank outside, the intensifier outside, and you would have what we call an enclosure or a chamber where you can put your food product inside, and then you can compress to a certain pressure that you would like it to be. Okay, so some of the commercialized HPP available in the market are Abdul technology. This was made in the United States. Okay, and it has basically a chamber that looks like this, and so it's a bit limited, although the chamber looks bigger, but the vessel for the food product is quite small. So, but I think the biggest size is about 5 liters. We have one here in Malaysia. Is in under what the Research Institute of Materi. Okay, and we have tried on a lot of food products that are available here. And UPM just bought another version of this, a bit bigger size, and we are leasing it to other companies or industry that is very interested in learning on this technology. Okay, other commercialized HPP are hyperbaric. This one from Spain. Okay, so the standard HPP industrial equipment. This is a horizontal design for traceability and easy installation. And of course, you would have the working pressure up to 600 megapascal. Okay, and this is hyperbaric statistics of where their product was being used Okay, 58% was being bought by American company, and the rest of it basically combination of Asia and of course the Europe countries. Okay, another one is made by Multivac in Germany. Okay, so it looks very sophisticated and very clean, and basically your product will come in from this side of the opening vessel, and then it will go in, and then you would have the pressure, okay, and then it will go out to the other end. So the cycle duration in minutes is about 7 to 8.5 minutes. Okay. So the processing operation, talking about high pressure processing, of course, we're talking about pressure. So the basis for applying high pressure to food is to compress the water surrounding the food. So the water being the medium of it. And at room temperature, the volume of the water decreases will increase in pressure. Of course, it's being compressed, correct? And because of the liquid compression results in small volume change, high pressure vessels using water do not present the same operating hazard as vessels using compressed gases. So it's quite safe. Okay. The only disadvantages to this process is that it has a very long holding time before and after the treatment. Okay, because we want to keep the product not to keep the product, but basically to keep the environment at the safest level, and for the pressure to build up as low as we can, and it's not, inflicting safety issue to the operators and so on. Okay, so the capacity of high pressure plant depends on three factors: the number of cycles that can be performed in a given time, the volume of the product, and the number of high pressure vessels available. So the more you have, the faster you can treat your food product. Because the thing is, because you need a cycle time that is determined by the time needed to handle the food product. So basically you would need to load your product, and then you need to wait for the pressure to come up or to build up. And then for the pressure to be treated onto your food, and then afterwards you need to wait for the pressure to go down again to the safest level, and then after that you need to unload it. So that the whole cycle that would take up a lot of time. So the productivity of the batch system is increased by reduction of the pressurizing and decompressing cycle. If you could eliminate both of this together, or maybe minimize it to a very minimal level, then you can make the process faster. And of course, the pressurizing time is reduced by increasing the delivery rate of the pump, and when required operating pressure is attained, the pumping rate is reduced. You can read more on this on my slides, but the gist is basically that, right? So another thing that you need to know is about the optimized packaging. So when you have a vessel and that looks something like a cylinder shape, whether it's vertical or horizontal, the most important thing is on how you will optimize packaging. So the packaging is recommended this way. Okay, so poor design, something like this. So usually we recommend something that is very flexible. Okay, so economically it must achieve for 75% loading for it to have a very good ROI, return of investment. So the HPP packaging requirement is a flexible packaging, which a 15% contraction, extra tight seal. You don't want any water needed to go inside your food product. Rounded and reinforced edges with minimal head space. And of course, if you like to incorporate MAP, it is possible. But your packaging needs to be very good at withholding tear, puncture, or surface smoothness, generally not affected by HPP. And often flexible pouches and bottles are inserted in the secondary cardboard containers after processing. So it's a bit like retort processing, okay, if you are familiar with it. Usually we put it into a flexible pouches after it has undergone a HPP process. You put into another secondary box for the packaging. Okay, so the processing operation, depending on, again, the objective of your food processing. So depending if you're talking about mollusk is something like shellfish, something like clams, abalone, the ones that have shells. Okay, so if you want to shucking, or what we call deshelling, then you can use it up until 300 megapascal at about 2 minutes only, the holding time of it. So basically, once you have that, all the meats at the inside, the shellfish are easier to take out, some things like lobster. Okay. So if you're talking about non-thermal pressurization, it is usually recommended between 400 to 600 megapascal and at a average time of 5 minutes of holding time. Okay, so this is some of the example. If you take a look at this, so and this is frozen meat. Okay, control when it is fresh, it looks something like this, but when it is frozen, it looks something like this. But when you put it, you treat it with HPP, the frozen ones doesn't lose as much color as it does in the fresh ones. Okay, because it still looks a bit more fresher than the fresh one. So the effects of HPP basically depending on the types of microorganism that we like to treat. Okay, so the gram-positive would eventually have a thicker layer of what we call the peptidoglycan. Okay, so it's much harder to treat gram-positive bacteria in comparison to the gram-negative bacteria. Okay, so the issue with the challenges, okay, with HPP is that we can have either of these three. Okay, so let's say if you were to have a vegetative microorganism and you have undergone HPP treatment and all the microorganism has died, then it is very good. But there's always a possibility after the HPP treatment, there is what we call the SLI state or sublethal injury. And this microorganism can be revived, can regrow again. Okay, so that's what we call a potential food safety risk. And also another state is what we call the viable but non-culturable state. So if it's been kept at a favorable condition, resuscitation of the microorganism may induce growth of the microorganism even after the HPP treatment. So basically, if we were after testing our product with HPP and we see all this SLI or VDNC state, we would recommend what we call a hurdle treatment. So hurdle treatment is maybe combination of other non-thermal methods or maybe combinations of acidification, combinations of preservatives that may help for the food to have a very safe HPP food. Okay. So again, microorganism and temperature also has an effect. Okay, so the temperature during pressurization can have a significant effect on the inactivation of microbial cells. If you look at this figure here, effect of temperature on pressure inactivation of Pseudomonas in 150 megapascal, 20 minutes. This one is Cytobacter and Listeria innocua at a different pressure and of course a different time frame. Okay, so basically depending on it, okay, sometimes even after a certain period of time, the microorganism can grow again. Okay, even after a pressure that has been done on it. Okay, so freezing temperature in treatment ranging from 100 to 400 megapascal for 20 minutes will enhance microbial inactivation when compared to high pressure treatment at 20 degrees C. Okay. Food matrix or food composition also play a very important role in making sure the effectiveness of HPP. So it really depends, and many researchers have stated that many food constituents appear to protect microorganisms from the effects of high pressure. Okay, so therefore it's very important to evaluate HPP treatment for each individual case. So non-nutritive solution reduce the microorganism barotolerance and enriched media protects microorganisms against pressure and suggested that free amino acids and the vitamins that are available inside the food product sometimes may again revive or maybe resuscitate the microorganism that was injured previously. Okay. And of course, if you look at the microorganism and inactivation kinetics, the pattern of inactivation kinetics is influenced by pressure, temperature, and of course, the composition of the media itself. Okay, and enzyme has been shown to have a very effective effect against the HPC, which we are able to inactivate to a certain state level. Right, the cost in implementing HPC are usually in the capital cost. Acquiring HPC is very, very expensive, let alone to maintain it, and especially when we're talking about the electrical cost, is very expensive actually, but the ROI is quite good in the sense that I have seen a couple of industry that managed to win back the ROI after 3 years or sometimes after 2 years because of the product that is very high quality and the ability to prolong the shelf life of the product itself. So obstacle in implementing HPP is basically the low level of public knowledge about the technology. Okay, so lack of explicit support for wider use of the technology. Okay, especially in Malaysia, even when we bought the equipment from Germany or maybe from United States, we need to have their engineer to come here for commissioning, for maintenance, for troubleshooting. So it's not quite viable in that sense. Okay. And of course, the image of high cost and the false image of high technological sophistication. It looks very sophisticated, but it's quite easy to operate actually. And of course, the reduced number of supplier of the equipment. Okay, so previously we have talked about only 3 industrial producer of HPP at the moment, and of course the perception of economical risk. We doubt about the mechanical and the structural reliability, the obsolescence of the technology for the first revision, especially the initial high investment cost, and of course the lack of after-sales service. And for bulk processing, the high pressure equipment should be part of the aseptic line, and parts of the contact with the food should be clean and sterile. This is sometimes can be a bit of a hurdle, especially for a company that has been established and part of their processing is not in aseptic processing, so they have to modify, and there's going to be a longer downtime for it. And in the engineering challenges to the application of high pressure primarily relate to the construction of pressure vessel. Okay, and we are relating it to safety. And of course, the pressure vessel should have a very short cycle time, easy to clean, and safe to operate with accurate process control. Okay, so that is it with HPP. Next is what we call the pulse electric field. Okay, so recently, previously, pulse electric field was only used for liquid food and for semi-liquid food. Something like tomato sauce or chili sauce that is quite viscous. They will call it semi-liquid food. It was previously used with pulse electric field, but now the technology is moving towards the solid food. Especially in Netherlands, they have started to treat sweet potato and potato itself, and even tomato here. So what is pulse electric field actually? So inactivation of microorganism and enzyme contained in food products by electric discharge began in 1920s. And with the electropure process for milk, which consisted of passing an electric current through in carbon electrodes and heating milk to 70 degrees. Okay. If I may say this, pulse electric field actually does not differ a lot from infrared, okay, and or even the technology is a bit same, okay, except that pulse electric field is using electromagnetic field in comparison to maybe radio frequency, although it uses an electrode, but it's what we call use a sound wave instead of an electrical energy. Infrared uses an electrical energy, but it was changed into a light energy. So that's the difference between those three. Okay. Although it uses the same technology, basically 2 electrodes, and the food product moves in between 2 food products, but the technology differ in that sense, right? Okay, so little effect of electrical discharge was demonstrated on microorganisms when the applied voltage used to treat food was increased to 3,000 to 4,000 volts. So it looks something like this. So basically what you will get is an irreversible cell death. Okay, so basically you will not have any cell that was injured that can be revived or regrow or resuscitate. Okay, the inactivation of microorganism was attributed to a shock wave generated by an electric arc that prompted the formation of highly reactive free radicals from chemical species in food. So non-thermal lethal effect was demonstrated on bacteria such as E. coli, Staph aureus, Micrococcus. Okay. So in general, an increase in the electric field intensity and the number of pulses lead to an increase in inactivation of microorganisms. So other factors that influence microbial inactivations are the treatment temperature, the pH, the ionic strength, and of course the conductivity of the medium. So depending on what type of food product that you are treating with pulse electric field, it would give you a different effectiveness. Okay. So it basically involves an application of high voltage between 20 to 80 kilovolts to food that is placed between two electrodes for a few micro to very milliseconds. And the process is based on pulse electric current delivered to a product placed between a set of electrodes, and the distance between the electrodes is termed as the treatment gap. Okay. Basically, you would have an external electric field that is used to exceed a critical transmembrane potential of 1 volt. And this results in a rapid dielectrical breakdown and conformational changes in the cell membrane, which leads to release of intercellular liquid and cell death. And PF also show changes in tissue structure, leading to weight increase and greater water holding capacity and less loss during cooking. This one was shown in a research using potato chips, or French fries. The processing time is calculated by multiplying the number of pulses times the effective pulse duration. So it looks something like this. Basically, you would have a HVDC, direct current, and you would have the energy storage capacitor, the wave controller, and the treatment chamber. Okay. And there are two types of pulse electric field. One is what we call the lab pulsar. So it's basically something that is gives out a very high voltage and it will die down. So it's exponentially decaying. And another one is what we call the treatment chamber, which gives out square wave pulses. The square wave is much more stable and it is much more efficient in treating or killing the microorganism inside your food product. Okay, so the engineering aspect of pulse electric field looks something like this. Basically, the configuration depending on the food that you are treating. So basically, you would have two electrodes. Okay, so you would have one type where your food product moves downwards or upwards, and basically you would have the electrical arc moving in zigzag motion in between these two electrodes. Okay, and sometimes you could have three electrodes. Okay, much bigger electrodes in the middle, and the less thickness electrodes on the left and the right side of it. And your food product can be flown in, okay, whether from the top or from the bottom. And again, the electric arc will come out in zigzag motion, okay, zapping all the microorganism or whatever else inside, okay, to make sure the safety of the food is reached. And there's another way of what we call the collinear configuration. So you would have this electrode here, here, and here, and then you would have somewhat like a wave. Okay, depending on the food product, if you don't have a lot of pulp, a lot of a lot of soluble solid or non-soluble solid inside, you will need to check with the configuration of your pulse electric field. This is basically the very basics of pulse electric field. This is what it looks like. So you would have the pulse electric generator, and it will give out electric arc in between these two electrodes. Okay. So the mechanism of microbial inactivation is speculated to have about two methods. Okay, one is what we call the dielectric breakdown. Basically, the cell membrane is considered as a capacitor. Okay, so by exposure to an external electrical field, okay, it was induced by movement of charges along the electric field lines and resulting in what we call the viscoelastic deformation of the cell membrane. Okay, so basically you need to find out what is the critical or the electrical strength of your microorganism. Okay, so if the E from the pulse electric field is much higher than the critical, basically would have a bit of a reversible process, okay, where your microorganism may resuscitate, but if it's much higher, then it is, would result in irreversible process. Another step of or another mechanism of microbial inactivation is in what we call electroporation. So what it does is basically all this electrical zap would induce pore or lubang melubangkan pada you punya microorganism. So what will happen is that microorganism would have very, very small lubang, and the water would goes inside this microorganism, will make it swell or make it bengkak. Dan lepas tu, what happen is what we call the membrane rupture of it. And eventually you will get an inactive cell. Okay, so this is another way of the mechanism where we assume what happened was the photochemical, the light or from the electric is a bit like macam petir atau lightning pergi kepada microorganism yang merubah DNA microorganism itu sendiri. Bila ia merubah microorganism DNA microorganism itu sendiri, yang menyebabkan microorganism itu tidak boleh lagi tumbuh atau resuscitate or even revive. Okay. So the main processing parameters is basically the electric field strength. So semakin tinggi EFS, semakin tinggi microorganism akan dibunuh. Okay. Tetapi jika semakin tinggi pun sometimes tidak bagus pada kita punya food product because dia boleh merendahkan food quality. Right? So this is the tough pulse electric field inactivation of listeria in whole milk. Okay, so the higher the electric field, the lower the destruction of your microorganism, okay, or the lower the microbial count inside your milk. So treatment time, specific energy, and of course pulse geometry we have discussed before. So kalau square pulse wave lebih efektif daripada exponentially decaying. And treatment time, of course, bila lebih semakin tinggi treatment time-nya semakin bagus. Tapi sometimes when we treat milk, for instance, macam saya ada buat research berkenaan susu, bila kita terlalu tinggi sangat dia punya EFS atau terlalu tinggi sangat dia punya treatment time, what happens to the susu, dia bau macam terbakar atau caramelize. Okay, so tak berapa bagus juga because terlalu banyak energy being given to the milk. Of course, conductivity of your food product. Okay, one of the key parameters is also a function of medium temperature. So media rich in ionic species such as tomato juice present problems in achieving a significant voltage to a supercritical field strength. Till smaller peak field strength is generated across the treatment chamber. Okay, so kita tak nak makanan yang terlalu berionic macam tomato juice or berionic ataupun acidic. Even sugar cane juice is not recommended for pulse electric field. It's not recommended. It's not effective. Okay. Effect of air bubbles. Okay, you shouldn't have any air bubbles inside your electrode because the air bubbles cannot withstand the high field strength, and of course, sometimes that can cause a significant drop in the field strength that will cause food safety problems. Okay, so you see this is the treatment time. Okay, same of Listeria monocytogenes in whole milk. So you would see this one at 25 degrees C, this one at 50 degrees C. 50 degrees C is effective in killing the microorganism, but however, at about 25 degrees C is not so effective. Okay, cell characteristics, of course, again, going back to HPP just now, in general, gram-positive organism, because of the thick peptidoglycan layer, it seems to be less sensitive towards CEF, so higher efficacy can be achieved in cell in logarithm growth phase, and it's not possible to sterilize. Okay, even with my research with goat milk, it's not possible to totally sterilize the goat milk. So hence we have to recommend a mild heat treatment to be used with pulse electric field. Okay, so aspect to be considered, of course, the generation of high electric field intensity, and of course the design of chambers, the electrodes, the gaps of the electrodes, berapa jauh. Kalau semakin jauh, semakin kurang effectiveness. Semakin dekat semakin bagus, tapi sometimes menyebabkan makanan kita cepat oxidize, ataupun kadang ada bau, macam saya cakap tadi, bau hangus, caramelize. Okay. And of course, if you were to compare pulse electric field with high temperature, short time pasteurization method, okay, so kalau you lihat kat sini, although the heat treatment is effectively kills off all the microorganisms in comparison to the pulse electric field, however, the results of this for this orange juice is not as good as the pulse electric field, where pulse electric field managed to minimize the quality degradation, especially on the vitamin C, the color, and so on. Right? And of course, you look at this, the slower browning effect of the pulse electric field in comparison to the heat treated orange juice. Okay, so this is some of the commercialized pulse electric field. We also have one here in Materi that we have highly researched on. So my latest research was on goat milk. But recently I've moved to extracting bioactive compound from using the pulse electric field. So we have yet to see the result of it. So soon, hopefully, right? So this is some of it. So this one is being used to treat potato, not potato chips, but the vegetable potato, rounded shaped potato. Okay, so basically, what does it do is that for every product or potato that was being treated here, they have better structure when it is being produced as a potato chips or French fries, we call it. Okay. Okay, so this is the pulse master. This is what I meant just now. So all the potatoes like to have a better structure, more flexible, and it's not tak senang patah. Jadi you punya marketability is higher. So unexplored, there are many possible project development designed to unknown destruction kinetics of microorganisms. Okay, identification of proper indicator organism, uniformly delivered treatment, because there's no specific standard for every food product, because sometimes food products are being contaminated with different microorganisms, and different microorganisms would have give out different results. Okay. Power ultrasound. I have to move a bit fast. It's already 3 o'clock. So, okay. So principle of ultrasound is basically it uses a sound wave instead of electrical arc just now, or instead of pressure just now when talking about HPP. So based on the sound wave, it has specific characteristics that you need to achieve for you to achieve food safety. Okay, if you look at this wave down here, okay, so the infrasound would give out much higher frequency in comparison to the human hearing, and of course in comparison to the ultrasonic power and diagnostic. So we mostly use to treat our food product, especially for preservation, in what we call this category as power ultrasonic. Okay, power ultrasonic would mean higher power. Higher power would mean lower frequency in comparison to the frequency that is being used in the diagnostic category. Diagnostic category are being used for ultrasonic to see the insights of your food product, or even for scanning of pregnant mothers. It uses the same technology as the one that we use here. Okay, so ultrasonic waves are similar to sound waves, but their frequency is far too high for perception by the human ear. and transmission of sound occur to the ordered and periodical movement of the molecules in the media with motional energy passed to adjacent molecule with transfer of matter. So ultrasound has property of sound waves such as reflection, interference, absorption, scattering, and can be propagated through solid, liquid, and gases. Okay, so you would have the direction wave, and that sometimes can be in this way, is what we call the longitudinal wave. Sometimes it can be what we call the shear wave. So most often we would use shear wave in comparison to the longitudinal. Okay, so these are some of the velocity of transverse and longitudinal ultrasound wave in different material. So different material would give out different velocity at a different wave type. So another wave characteristic is that it's depending on the medium. So if you look at this table on the right, depending on the medium, let's say hydrogen or maybe hydrogen gas or even liquid glycerol or seawater, it would give out different velocity. Okay, so what does it mean is that it means for every food product that is being treated with ultrasound, it does not necessarily would absorb the same amount of energy as the other food product. Right? You can read more here. Okay. What I would like to focus is on the two types of cavitation. So cavitation is basically what we call the gist of ultrasound technology. Okay, so you would have the stable cavitation and of course the transient cavitation. For stable cavitation, you would have compression and rarefaction that would happen to the molecules of your product. These molecules can either be your food molecules or sometimes can be the microorganism molecules. Okay, so the microorganism. And so this frequency will give out, the positive frequency will give out compression and rarefaction. So rarefaction, your molecules or bubble formation would be bigger, and compression will be smaller, and as it moves further on, the bubble would become bigger and bigger. For a stable cavitation, sometimes it may not proceed to the transient cavitation. Sometimes it becomes that way only. Okay, just small bubble, bigger bubble, small bubble, bigger bubble. But for transient cavitation, what happens to the bigger bubbles is that eventually it will implode. So you would have implosion that happens inside your food product that is being treated. Okay, and this bubble implosion sometimes can form up to 5,000 Kelvin, but because of the temperature that is what we call very minuscule for the bubble, so hence there's no temperature increase on the ultrasonic or treated product. Okay, so different liquid flow or bubble movement can also affect the effectiveness of your food treatment. Okay, so microstreaming occurs due to growth and shrinkage of the cavitation bubble during cycles of rarefaction and compression. So what microstreaming is that? This one, when bubbles increase in sizes, and of course when bubbles decreases in sizes. And the rapid movement of liquid causes by changing bubble size, causing shear. So this shear pressure is the one that causes your microorganism to die off. And the effect is limited to about 1 bubble diameter. And there's also what we call the microjet. Okay, what happens is when you have a transient cavitation, when this bubble implodes, it would give out what we call a microjet. Okay, microjet is basically a very high pressure water, okay, produced at a very high temperature. And of course, there's another thing what we call the acoustic streaming. So what is acoustic streaming? Is basically a sonochemistry. So sonochemistry is ultrasound that produces a range of effects on chemical reaction in treated material, including free radical formation, increased reaction rate, less extreme processing condition, and reduced induction period, easier initiation of a difficult reaction, improved catalyst efficiency, and permit use of less refined raw material, and so on. Okay, but what does it look like is basically, it gives out something like this. So sonoluminescence from cavitation bubbles can look something like this, and of course, using an ultrasound, we can also produce what we call the sonocrystallization. Okay. So sonochemistry happens, okay, when you have a low frequency and you would have cavitation bubbles, and high frequency, your bubbles would reduce in terms of size and carry less energy. And sonoluminescence happens in between the skin. Okay, so it's a transient bubble collapse that emits light and causes sonochemical reaction. Types of ultrasound, there are two. Again, I've mentioned before, low power is for diagnostic, okay, measurement of thickness, measurement of flow rate, determination of composition, particle size, or even ultrasonic imaging. We're talking about high power, generally in the range of 40 kilohertz. It is used for drying and filtration, can be used for microbial and enzyme inactivation, disruption of cells, degassing of liquid, extraction process, and many more. Okay. There are two different components of ultrasound. There are what we call the bath type, and there's also what we call the probe type. So the probe type looks something like this, where you would have your probe here that would give out frequency of your ultrasound. Okay, so it's very limited to a localized diameter. So if your probe is very small in diameter, hence it will give out a very small frequency diameter too. Okay, a bigger diameter or bigger exposure to ultrasound would look something like in a bath, but in a bath is what we call an indirect ultrasound. In comparison to this one, it's what we call a direct ultrasound. Okay, whether or not it is efficient for your material is really depends on you. Okay, so let's say if you want to have a direct ultrasound treatment, a faster killing mechanism, then you can use the probe type. If you want to use indirect ones, then you would have a lower rate of killing the microorganism and so on. Okay. So critical parameters, again, the amplitude of the ultrasonic wave, the exposure or the contact time with the microorganism, the type of microorganism, okay, whether you are dealing with gram-positive or gram-negative, the volume of the food to be processed, and the composition of food, and of course, the temperature of treatment. Okay, so general application is basically for antimicrobial treatment, enhancement of mass transfer, basically when you're talking about increasing the rate of mass transfer in drying, okay, brining, membrane separation, dewatering, and bed filtration, or maybe talking about drying your product, okay, dehydration, enhance of heat transfer, okay, so talking about dehydration your product, what else, increasing the rate of freezing or thawing for that matter, and for cooking, processing of protein food such as meat tenderization, what else, if I'm not mistaken, protein food, not just on the meat tenderization, but also on the thawing of the frozen chicken, okay, such the application of it. And of course, we are using ultrasound as a processing aid to homogenize your food product. Okay, let's say if you have oil and water emulsion, you want to make it into mayonnaise, then you can use ultrasound. Okay, so application of ultrasound, of course, suggesting that chocolate milk offered significant protection against microbial inactivation again. So these are some of the limitations of the ultrasound, where this media inside your food product can become a resistance towards the efficacy of your ultrasound product. And of course, if you were to combine treatment with other methods, the combination of the treatment can improve the efficacy of the treatment. Right, and drying process, okay, you can read more on here. This is the drying of carrots. This is food drying process using a power ultrasound. So depending on the power, okay. So the higher the power, much faster the drying process. This is a muscle, the beef muscle, otot lembu yang was being treated with ultrasound. So you can see, okay, basically it is disintegrating the fiber bundle. So basically you would get more tender beef product. Okay, so these are some of the industrial application of ultrasound. Okay, there's a link, there are 3 links here that you can take a look later on. Okay, so this is the industrial application, so it's quite big, and depending on the transducer type, you can induce a very homogenized frequency or otherwise. Disadvantages, of course, again, lack of standardization. Okay, direct contact between probe and food medium. We don't want any food safety risk. Okay, effect on color and antioxidant has been reported because of the ultrasound mechanism is that it would make the color to separate from your food product. It is good color you want to extract the color, but it's not good when you want to retain the color inside your food product. But then it can also causes what we call a rancid odor in the processing of vegetable oils, especially when producing mayonnaise using ultrasonic. Okay. So irradiation, what is irradiation? Irradiation is a technology that improves the safety and extend the shelf life of food by reducing and of course eliminating microorganisms and insects. So like pressurizing milk in canning fruits and vegetables, irradiation can make food safer for the consumer. And FDA is responsible for regulating the sources of radiation that are used to irradiate food. And FDA approved the source of radiation for use on food only after it has determined that irradiating the food is safe. Okay, so irradiation is the only technology or the only non-thermal technology that are being regulated worldwide, even in Malaysia. Okay, so the history of it is because in 1901, first food irradiation was patented in the United States and Europe. Basically, at that time, we were moving towards the World War, and of course, you want to irradiate your food to preserve it much longer for food security purposes and so on. In 1965, world first commercial irradiation plant for food processing commissioned in Canada. And in 1992, the first US commercial food irradiation plant shipped irradiated strawberries to 5 states and 2 foreign countries. And now the food is getting the irradiated food is getting higher by the day because it is being exported throughout the world nowadays. Okay, so why food is irradiated? Mainly because of the food waste that we are facing. Okay, so if you take a look at this food product, especially agricultural food product, talking about bagged salads, the total food waste is about 70%. Bakery food product about 50%. Bananas, just bananas alone is about 20%. And the apples that we see for about 40%, and grapes for about 24%. So hence the usage of irradiation is not just to prolong their shelf life, but of course for disinfection on cereals and sprout inhibition on potato, onions, ginger and garlic, those types of products that can grow after you harvest them. Okay, and what else? Pathogen reduction, of course, especially in spices, and disinfection in pulses or in legumes, in kacang, and of course dry fruit. Because sometimes the issue with this kacang ataupun dry fruit, you would have kutu dekat dalam makanan tersebut. So by using irradiation, you can eliminate them altogether. And of course, for quarantine purposes. For countries such as Australia, they are very strict because they're an island, and if something were to happen to their agricultural food product, they would have no food left to eat. So basically, they are very, very strict on this regulation. So what are the sources? Basically, you would have cobalt 60, cesium-137, which is the gamma ray, the traditional one. Okay, up to the 95% of emitted energy is available for use, and it penetrates deeply and yield a very substantial uniformity of the dose in the food product and considered to pose low risk to the environment. So another type is what we call the electron beam generator, or we call it e-beam. Okay, so this one is concentrated, accelerated to 99% of the speed of light, and energies up to 10 MeV. Okay, because of the e-beam are generated electrically, they offer a certain advantages, which is they can be turned on only as needed, and they do not require replenishment of the source, such as cobalt-60, and there are no radioactive waste. But the disadvantages of e-beam is because of the shallow depth of penetration. It can only be absorbed by a certain amount of your food product, and the e-beams must be converted into X-ray to penetrate larger items such as carcasses. And of course, we would use a high electric power consumption. So another sources is what we call the X-ray. Basically, from e-beam, you can turn it into X-ray form. And the advantages of the X-ray are penetrating and can be used on food boxes 15 inches thick or more, which allow food to be processed in a shipping container. So this is what the e-beam looks like. So you would have a very homogeneous e-beam particles in comparison to the X-ray, but the X-ray can penetrate much thicker food products. Okay, so again, these are the sort of the sources that you have. So gamma ray, basically most popular, simple, easily controlled, widely available. But then it has a radioactive waste in comparison to the e-beam and X-ray. Okay, so radioactive dose are basically the quantity of radiation that is being absorbed by the food, which is what we call the gray. And 1 gray is about 1 joule absorbed per kilogram of food. So international health and safety authorities have endorsed radiation level up to 10,000 gray. Okay, the desired dose is achieved by the time of exposure and by the location of the product relative to the source, and the amount of energy absorbed by the food will also depend on the mass, bulk density, and of course the thickness of the food. So these are the thresholds. Okay, basically the maximum limit that it can absorb radiation before it develops an off flavor. Okay, and the effect of radiation is basically onto the DNA of your food, and of course on the microorganism itself. Okay, so this is what happened to the cells. Okay, so to the microorganism, what they will do is basically cells are damaged. It cannot be repaired, and it will, even if it's repaired, it will operate abnormally, and of course it will die as a result of the damage. Irradiated food list. These are the list of food that is being irradiated. Okay, Australia has a longer list in comparison to Canada. And cost of food radiation is basically the capital cost of it. Okay, the typical food irradiation plant was 3 to 5 million, and this was years ago, and I'm sure it's much higher now. Okay, because it is regulated. So any food product that is being irradiated, it has to be marked with this logo. They have to have a Radura logo. Okay. And these are the type of food product that is being irradiated. So this one is not being irradiated, and this one is being irradiated with a gamma ray. Okay. And the public acceptance, it takes years for people to accept it. But even now, there are basically a campaign to boycott this irradiated food product because they felt like this radioactive is not good for their product. So do not nuke our food. Stop food irradiation. This is one of the campaign in the United States. But then again, speaking logically, even Louis Pasteur discovered pasteurization in 1850, and it took nearly 70 years for it to be fully accepted in United States. So even more so when it comes to irradiation, we just have to be very patient with it and just make a lot of public awareness in regards to this. So these are the acceptance in the scientific area. 55 countries have approved uses of irradiation, including Malaysia, and I think Indonesia too. Okay, so these are the data collection by the International Atomic Energy Agency. Okay, so these are the countries that have started to irradiate it on their food products, especially on the poultry, on the beef, and on the chicken product. What does the facility look like? Most of them look something like this. So basically, you would have your radiation source that is being um, submerged in underground. Okay, so you would have your food product being transported with a forklift onto a conveyor system. This conveyor system would move your product and then it would submerge it into a radiation pool. Okay, so you would have radiation with water as the medium. Okay, so again, this is one of the method of doing so. So you would have the conveyor and you can just submerge your food product and then you take it out and then it will be moved somewhere else. But the caveat of this is that the facility has to be very, very safe. Even the concrete wall needs to be at least 6 foot thick. Okay, at least ketebalan dindingnya perlu at least 6 kaki. Okay, so that is it for food irradiation. Moving on to the next topic is ultraviolet and pulse light. Previously, I am not very familiar with pulse light. Actually, I have not been involved with the research in pulse light, and I thought, pulse light is actually the same as pulse electric field. But although the name is a bit the same, but when I look at the mechanism, it's much more similar to ultraviolet. Okay, the difference is that ultraviolet uses what we call a continuous light exposure to your food product, but the pulse light is something that is discontinuous. Is you boleh turn off and turn on, turn off and turn on. That is what it means by pulse. Okay. So previously, UV was only being used as a water treatment for air disinfection and surface decontamination. But of course, we have moved past that. We have used it onto the liquid food. So the liquid food have range of optical and physical properties and diverse chemical composition that influence of UV light transmittance, dose delivery, momentum transfer, and consequently microbial inactivation. And what does it say is that when our food product has a lot of composition inside, I'm talking about non-soluble solid, soluble solid, the vitamin C, the sugar, and so on and so forth. So those things would have an effect on the efficacy of the UV light or even the pulse light itself. Okay, so the critical factors of it is the same, okay, as we have talked in pulse electric field, basically the transmissivity of the product, meaning the readiness of the product to absorb the energy, and of course the geometric configuration of the reactor, the power, the wavelength, physical arrangement, product profile, and of course the radiation path length. Okay, so UVC is part of the electromagnetic spectrum between 200 and 280 nanometers. It is suitable for fruit juice stabilization since it has a positive consumer image and it is attractive to the food industry due to its low cost. Okay, so what does it do is basically it penetrates. It has a light that penetrates the food material up until to several millimeters, depending on the optical properties of that food. Okay, so the moderate amount will disinfect your liquid food up to 5 log reduction of pathogens, and you minimize the changes in color and of course the overall sensory score. And the best part about ultraviolet is you can use it for surface decontamination of your fruit or even vegetables. Okay, so you can increase the shelf life and you can reduce the post-harvest rot or ripening. The mechanism is basically again the same with we have talked previously. Okay, is about affecting the DNA of your microorganism. Okay, so these are some of the usage. Okay, I think UVC find its popular status during the COVID area. I think everybody has it because they want to sanitize their food product, their surface counters, sometimes even the toilets and our office tables and so on. But it has been used to surface decontaminate also the pizza base, okay, or even on your fruit. Okay. So for liquid food, the usage of UVC would be very efficient when you use it onto a turbulent flow rate. For a laminar flow rate, it's not very efficient, okay? Because it is a physical method, it leaves no harmful chemical residue, and of course, the flavor of the food is not affected, right? And US regulation has only approved the usage of ultraviolet as a pasteurization method in 2050. Okay, and the types of UVC reactor look something like this. Here again, I've mentioned before, so it's much more efficient if you were to use it in a turbulent flow. So the turbulent flow product is much more efficient, and if you were to have more of your light source, you can disinfect a lot more surface area. Okay, something like this, Taylor coax flow, where you have a rotor that can move, okay, it will circulate, then all your liquid food would be minimized to a very thin layer, and it will be exposed to the UV lamp at the side. The DIN vortex is basically a technology that uses a convoluted tube. So you would have the UV lamp that is inside of it. Okay, so you would have your juice to be circulating around and increasing the surface area. Okay, so the highest reduction was found for 8-log reduction for E. coli in a gene reactor used for milk pasteurization. And these are some example of it. Okay, so basically UV light uses a LPM or LMP also can. Okay, low pressure lamp, right? As opposed to the visible light or the lampu Kalimantan kalau digunakan kat rumah itu. Okay, that is what we call the visible light, right? Okay, move on to the cold plasma. This is a bit of newer technology that has not been relatively used, even in industry, and it is only at the fundamental level at the moment. So plasma is considered the fourth state of matter. At a very high energy, matter transformed into plasma. So plasma consists of a mixture of neutral molecules, ion, positive and negative, and electrons, each with such a concentration that the overall charge of the mixture is zero. So plasma has all of these molecules inside, okay, such that the overall charge of the mixture is zero. So how plasma works is basically, again, you would use 2 electrodes, okay? Except in this case, it comes out like a gas, okay? So there's no electrical charge, there's no sound waves, and this time around, it uses what we call a very high energy gas, okay? So you would have this. So at the moment, it uses to surface decontaminated food product, okay? And the charged particles allow the plasma to be manipulated by electrical and magnetic fields, so it gives out this color, okay? So for plasma, it gives out a color that can be distinguishable. So the type of the color that the plasma emits depending on the type of gas that you use. So you can either use oxygen, you can either use CO2 or even nitrogen, okay? And it was being speculated that the the mechanism of killing mechanism of microorganism was not caused by the plasma itself, but it was caused by the ozone that was the byproduct of the plasma itself. Okay, so that was being speculated up until now. Okay, the plasma type that can get divided into thermal plasma. Okay, the temperature can be up to 11,000 Kelvin. This was actually a welding. Okay, so welding yang digunakan itu is the same as plasma, except with very high temperature, but it's not suitable for food application. And non-thermal plasma is basically the same as the neon sign and also the plasma TV that was being used in your home. And the temperature is about 300 to 1000 Kelvin, and it produces UV light and ozone. So that this is where it was speculated the killing mechanism of the microorganism. Okay, so generation of plasma, again, you can use oxygen, you can use nitrogen, you can even use helium or even argon. So the energy sources come from the heat, come from the electricity, radiation, and even adiabatic compression. Okay, so this is the mode of application where it is, if you look at this here, this is actually almond, okay, kacang badam. Okay, this is surface decontamination for food surfaces only. And advantages of it, the target can receive non-thermal plasma from multiple electrodes. The target can be about 5 to 20 centimeters away from the non-thermal plasma generating electrode and no electrical current through the target. So it's not like pulse electric field where you have the electrical discharge. This one does not. Okay. And the type of treatment is also suitable for irregular surfaces. So something like kacang badam, whatever types of nuts that you have is suitable for food decontamination. So direct effect, this one mostly being used on the salad leaves, okay, daun-daun salad, sayur-sayuran yang berdaun, okay. Since most food have high level of water, they can conduct electricity at high voltage level. So localized conduction may damage the food, and it is much more challenging to build and operate direct treatment plasma in comparison to the non-direct treatment. Okay. So microorganisms are exposed to the broadest combination of active antimicrobial agent at the highest possible intensity. And positioning of the food surface to be treated must be carefully adjusted to avoid point discharges, which can cause damaging levels of heat to be concentrated at a single localized area. Okay, the disadvantages of cold plasma is that it can induce what we call the cold and also hot spot. So there are areas that was not being treated with cold plasma, but there are areas that has been treated with too much cold plasma, which is also not good. And it can burn, akan hanguskan you punya food product. So the power process factor for antimicrobial, the power that was used, okay, the volume and speed of the plasma, position and the target in the NTP scene, the non-thermal plasma, the feed gas, depending on the type of feed gas, you would give out different intensity of the gas plasma and of course the nature of it. And again, as mentioned, the mechanism of microbial, it was speculated was induced by ozone or even the ultraviolet light, and sometimes it was induced by the destruction of the disease, destruction of the DNA by the disease. Okay. So these are the results of treatment of almond surface. Okay. Here in Malaysia, there was one Universiti Kebangsaan Malaysia, or what we call UKM. There's a professor that is actually treating a nut for reduction of aflatoxin using the cold plasma. And his research was quite marvelous actually. But at the moment it's quite limited still, but he is working on it. And one of the research is on the biji benih, on biji benih chili. So menggunakan ion plasma ni, dia mempercepatkan germination ataupun percepatkan pertumbuhan pokok cili on the treated biji benih tadi. Okay, so this are the results on treatment of cut fruit surfaces, which is on the cut mangoes and cut cantaloupe. Of course, with the higher plasma exposure, you would have higher destruction of the microorganism. Okay, this one is on gas plasma on E. coli. Okay, this one is on spore. The potential concern are basically on food product that has lipids and other sensitive constituents, such as vitamin C and vitamin E, which are still ambiguous. We do not know the true effect of it. And food product that have high lipid content would likely be affected by oxidation, resulting in formation of hydroxyl acid, keto acids, and short chain fatty acid and aldehyde. And of course, with gives you off flavor and rancidity. And of course, changes in nutrient content, color, texture, qualities, and toxic residue and other chemical changes too. Okay, you can take a look at the application of plasma through this YouTube link. Okay, I think this is the final subtopic of the day. Okay. Ozone is basically the only non-thermal that uses chemical reaction. Okay, so basically it is a gas that was induced from, that was produced from the oxygen as a result of lightning or UV light interaction. Here in UPM, we have a research that was done onto ozone, but we use what we call the corona discharge generator. So corona discharge generator basically sucks in the air from, sucks in oxygen from the ambient air, and it change the oxygen to ozone. So it is a very potent oxidation capacity that makes ozone very effective in destroying microorganisms. And it has been demonstrated to be effective in killing gram-positive, the one with the thick peptidoglycan layers. Previously, I've talked about this, right? So even that was effective against ozone treatment. Okay, so the two major mechanisms has been identified. The first mechanism is ozone will oxidize the sulfonyl groups and amino acid of enzymes, peptides, and proteins to shorter peptides, basically on the DNA destruction of the microorganism. And ozone will oxidize the PUFA, the polyunsaturated fatty acid, to acid peroxide. And the ozone degrades of the cell envelope in cell disruption, and subsequently it will leak the cellular content. So you would have, again, macam I mentioned tadi, macam menyebabkan lubang gitu pada you punya microorganism, and you will leak all the nutrient compound of that microorganism, making it die. Okay, so this is the ozone generator. So ozone, this is the corona discharge generator. Basically, again, uses two electrodes. Okay, so this electrode will zap the oxygen. Okay, and this is what we call the discharge gap. This discharge gap will zap the oxygen that turns into ozone. So if you want to increase the efficacy or the high yield of ozone, you just use another oxygen cylinder in comparison to just, taking oxygen from the ambient air. Right? So in 2001, US FDA has approved the use of ozone as a antimicrobial agent in the treatment, storage, and processing of meat and horticultural produce. And ozone at concentration of 0.15 to 5 ppm has been shown to inhibit the growth of spoilage bacteria such as yeast. Okay? And the polyphenol of the treated tropical fruits are not affected by the ozone at 10 to 20 minutes. So that's the advantages of it. But then it was theorized that the auto decomposition of ozone is accompanied by the production of numerous free radicals such as hydroperoxyl, hydroxyl, and of course the superoxide radicals. Okay, what does this do is basically it would induce the aging process of your food. So the ripening process would become much faster. Okay. Vitamin C has a significant negative correlation, meaning the longer exposure time, the more vitamin C was oxidized. So it's not ozone is not recommended for fruits that have higher vitamin C, such as mango, those cut fruits. Okay, the ones that still has the skin or kulit dia, kita recommend. Okay. Yesterday, I attend a talk by a professor in Thailand. He did a lot of research using ozone. One of the research was on longan or mata kucing, buah mata kucing. Jadi kegunaan ozon ni hanyalah untuk fumigate, maksudnya untuk replace the usage of sulfur dioxide previously. So buah mata kucing kan kalau kita mau export, jadi kita mau apa orang kata retain atau prolong the shelf life. So instead of using sulfur dioxide, we uses ozone to prolong the shelf life. And the result was very good actually, because the longan coloured kulit buah mata kucing itu lebih cerah, lebih cantik dan lebih appealing kepada consumer. Okay, that is one of the effect of the peroxide, hydroxyperoxide. Ini macam ada bleaching effect pada kulit buah longan tersebut. Okay. But ozone is not universally beneficial. In some cases, it may promote oxidative spoilage, and this is what I mean just now. So on cut fruits, it's not recommended to use ozone, but on buah yang masih ada kulitnya lagi, it is recommended. And another research that was done by the same professor in Thailand was that they try to disinfect buah durian yang diekspor ke negara China. Negara China agak paranoid buah durian dan datang dari negara ASEAN ini diimpact by coronavirus. Jadinya digunakan ozon sebagai cara untuk matikan atau disinfect the buah durian itu. Okay. So ozone uses in food industry mainly at the moment banyak digunakan sebagai pembersih, antara sebagai cleaning agent. So jadinya ozon yang dalam air dia boleh digunakan untuk bersihkan kilang-kilang seafood, kilang-kilang poultry, kilang-kilang beef, even untuk pembersihan ayam itu sendiri, pembersihan sayur-sayuran daripada menggunakan klorin. Okay. And application of ozone, it looks something like this. And this one in industry specs. So basically, they would use ozone, oxygen, and ozone generator with control panel, and it will be injected into a contact tank. So this contact tank would have water inside, and then it would be generated onto a conveyor belt where it can properly disinfect or clean up your food or food products. Okay, so antara aplikasi in industry, you can also take a look at this YouTube link. I think this is another industrial application of ozone. This one to disinfect apples. Okay. And in general, the gaps or the challenges in adopting novel food pasteurization or even non-thermal pasteurization is the process equivalency or the standard operation. And of course, the target organism of concern has to be determined along with the surrogate. Sometimes a secondary contamination can happen. So for that specific food product, you have to work along with the secondary infection. And of course, you need to know in detail the knowledge of microbial dose response behavior. Okay, and other things that you need to know is a complete representation of the distribution of lethal agent and velocity field for development of an accurate process model. And what else you need to know is about the chemical safety, process uniformity, process monitoring, verification, and of course validation. So these are the challenges in novel non-thermal treatment. Okay, so in conclusion, the introduction of NTT or NTT, non-thermal technology or non-thermal processing, is very timely in an age where consumers are vying for more nutritional, shelf-stable, cheap, and with less carbon footprint. But these technologies have been shown to be efficient and consistent in improving the quality of food, with potential of developing new products with unique functionality. And ensuring food safety and meeting nutritious food demands a better understanding of the complex physicochemical mechanism of non-thermal processing technology and their effects towards the physicochemical attributes and nutritional content of food. And the interdependency between the consumer needs and the new technology should be recognized and receive more attention in the modeling of food product innovation by the food industry. With that, I end my lecture. Thank you very much, everyone. If you have any questions, please ask away.
Okay, thank you very much, Dr. Nadiah,
Thank you, Ibu.
for giving us such an inspiring and also interesting presentation. Okay, and everyone, please ask if you have any question. Use the raise hand feature in the Zoom and then unmute your microphone and camera. Okay, I like to have 3 questions from all of you. Is there any? Okay. Okay, if there is no question, I will start to ask maybe Dr. Nadiah
No
for the
problem.
non-thermal and non-thermal processing. If we compare in Indonesia and about your slide, there is so many I think gap here in Indonesia. We just starting to research about the application. I'm not sure in food industry they adopt this technology. For example, maybe in National Research Agency in Indonesia, BRIN, they already developed cold plasma technology to extend the shelf life of fresh fruit. And then I also heard in Badan Atom Nasional, they already developed food irradiation to I think to inactivate the microbes in mango.
In mango.
Yeah, mango. They export the mango to Uni Emirat Arab. So there is some research, but I'm not sure that industry, I mean, in the big industry use this technology. Okay. And maybe one application about ozonization. Ozonization in our faculty. I mean, maybe two years ago, we tried to develop ozonization for cabbage. But now, yeah, we still have many difficulties about intensity of the ozone, and then about the design. So. And the last one is ultrasound. Ultrasound in our lab we have Isonica. Isonica is a probe type. Type probe type, and then we usually use this equipment to extract the anthocyanin and also to help the to breakage the cell wall before we extract the essential oil. So among all the technology that you already mentioned, we may be familiar in maybe for technology, but for pulse electric we never tried before. And then for pulse light and also which one? The last part, the plasma, cold plasma, we also never with this technique.
I think in a way Malaysia and Indonesia is not much difference in that sense. Okay, even our industry a bit susah untuk menerima sesuatu yang baru gitu. Macam kiranya selama ni sudah ada teknologi yang agak efisien untuk menghasilkan food product, kenapa mau pindah kepada new teknologi kan? Macam gitulah. So jadinya even saya pun sendiri macam having difficulties in making them confident to adopt new technology. Even not just the industry but onto the government themselves. Okay, for instance, we are talking about sebagai contoh lah ya, we're talking about MAT, microwave assistant thermal sterilization. This was a technology that was developed by Washington State University and dia dah commercialized, and kami sangat macam interested lah sebab for one thing, kita boleh simpan makanan selama 12 bulan, and then pada room temperature tak perlu simpan dalam chiller, doesn't need to be kept in refrigerator. So I felt like that is a very good idea, especially when we were once, we were once facing pandemic such as COVID, flooding season, even sometimes kadang neighboring countries macam like Indonesia, you guys ada natural disasters such as earthquake and so on, which is benda teknologi ini sangat bagus kiranya kalau kita ada, kita boleh study. Sebab one thing, perbezaan antara research that was being done by the Washington State University is that permakanan, food yang was being treated is different than from makanan yang kita biasa di Malaysia. Macam makanan ruji di Malaysia adalah nasi, dan selalunya ada kari daging, kari ayam, atau secara contoh yang paling senang, nasi lemak. Nasi lemak selalunya nasinya dimasak dengan coconut milk, and then you would have sambal, then you would have egg. So adakah cara penyimpanan yang kalau yang telah di-study oleh Washington State tu is going to be the same for our food product? We do not know. So that's why we propose the technology for us to research more, to give us the facilities for us to pergi naik Washington State untuk study benda-benda ini. Even untuk convince government untuk bagi kami macam travelling grant pun agak susah ya. Apa lagi kalau kita mau build confidence dengan kita punya industri. Sebab one thing, di industri tengok bila nampak mesin-mesin seperti ini, sepertinya dia macam terlalu sophisticated, terlalu, kalau in bahasa Melayu kita panggil terlalu canggih gitu. Jadi dia takut nak operate benda-benda tu. Lagi pula macam kalau kita talking about high pressure processing. High pressure processing dan berkait dengan keselamatan. Dan diorang pun takut nak operate because takut meletup, macam itulah. Jadinya I think it's a bit of a challenge to convince people, not just the public, but also the industry, but also the government to adopt this new technology. And unless we move forward, we will not progress much in the food development area. Although memang lebih senang kalau kita, orang kata apa, stick with the traditional methods of cooking. Masak aja guna dapur gas. Tapi kita kena mula tengok kepada future. Kita tak tahu what's going to happen. Kan? Makanan semakin mahal, food security becomes a big issue. We are also facing kemarau panjang katanya because of the El Nino. So kemarau panjang means makanan haiwan pun tidak boleh. Jangan katakan makanan manusia, makanan haiwan juga tidak boleh diproses. Jadinya bila makanan haiwan pun tidak boleh diproses, sumbernya agak limited, jadi makanan kita pun eventually akan melalui kenaikan harga. So these are the things that we need to educate people, and especially we need to educate our young people. Kadang-kadangnya kalau macam saya mengajar di food engineering faculty, kadang-kadangnya jadi laughing joke gitu dengan jabatan lain. Sebab apa? Jabatan lain, talking about mechanical, talking about aerospace technology, but people often forget that we eat food sampai bila-bila. We were not going to eat pills, or we are not going to eat ubat-ubatan, extract, anthocyanin for that matter, but we are going to eat food sampai bila-bila, because kepuasan makan itu pun something nikmat untuk seorang manusia kan. Kadang-kadang kita boleh makan, boleh bau, rasa, itu adalah satu nikmat untuk kita makan. Jadi sampai bila-bila, sampai kita mati pun, sampai kita ada anak-anak cucu cicit pun, kita masih memerlukan makanan. Jadinya kejuruteraan makanan atau teknologi ini perlu progress as teknologi lain juga progress. Itu pendapat saya lah.
Okay. Terima kasih Dr. Nadiah. Menarik Dr. Nadiah. If we're talking about food supplies, maybe for military food supplies,
yes, exactly.
they need to process to ensure the food is safety for maybe if the condition in maybe in war season or
Betul, betul.
yeah,
Kalau
managing-
kita lihat on that point of view, saya lihat United States, Amerika, dia sangat progresif in terms of that. Maksudnya, ya, makanan untuk para militernya sangat bagus sekali macam in terms of the health composition, makanan yang macam mana di-preserve. Kalau di Malaysia gini, masih lagi resort processing. Jadi
Betul.
kadang-kadang makanan tu tak berapa cantik kan, macam rupanya agak lembik, agak tak
Iya.
berapa menarik. Ya.
Makanan
So,
kaleng kalau di kami.
ya betul, betul.
Mungkin.
Jadi jadi pada saya moving into the 21st century, moving into the 22nd century. Jadi makanannya pun seharusnya moving towards that progress juga. Just bukan setakat untuk orang awam, but untuk military, untuk orang yang bekerja di hospital. Kadang-kadang tak cukup masa untuk makan kan. So kita perlu berfikir untuk benda-benda macam tu. Jadi innovativeness in food, not just in the food technology, seharusnya berjalan sekali dengan advancement of other technology.
I agree with you, Dr. Nadiah, and especially about the technology readiness level and about the what is called innovation. Yeah, in Indonesia we call pangan darurat. So the food that's used for maybe in situation critical situation like maybe disaster or yeah, we call pangan darurat.
Pangan darurat.
Yeah, it's very now the ministry also developing these issues to be the most important.
So kalau saya boleh tanya, di Indonesia kita adanya macam we call food bank or not?
Food bank.
Ya, macam tempat penyimpanan makanan in case of natural disaster. Ada.
Maybe student ada nggak
anyone yang tahu?
Dekat kalau di kami kalau ada disaster yang bertanggung jawab itu adalah SAR, badan SAR, SAR itu apa ya, rescue.
I see.
Agak lupa ini ya singkatannya. Badan
penyelamat macam gitu ya?
Ya, badan penyelamat. So they also have maybe like instant cold storage and I think it's good that kalau kita ada, kalau di Malaysia saya actually tak pernah dengar lagi food bank sebegini. Selalunya kalau badan penyelamat di Malaysia kita panggil NADMA. Kalau ada national disaster, jadinya dia akan panggil badan penyelamat di negeri lain untuk masakkan makanan pada victim di negeri yang affected. But kadang-kadang kita overlook the fact that what if satu Malaysia yang affected, then siapa mau bagi makan kan? We have about 28 million people in Malaysia itself. So yeah, to be honest, food bank I think is a must, especially during our time nowadays. Maksudnya lebih bagus ada gitu kan, tapi itulah caranya untuk mitigate macam mana mau moving forward dengan the teknologi tu, itu yang perlu di-strategize-kan lagi. Sama mungkin Dr. Nadiah, kalau di Indonesia gitu kalau ada bencana we maybe donatur only give mie instant or instant noodles.
Yeah, betul.
We don't want very low nutritious.
Low nutrition. Satu lagi ibu kadang-kadang air panasnya pun tidak ada.
Ya betul.
Jadi macam mana nak masak kan?
Ya betul. Itu jadi perlu ransum or maybe instant but very high nutrition.
High nutrition, especially bila kita dalam natural disaster macam gitu, kadang-kadang orangnya pun macam agak lemah kan in terms of immune system. Antara satu benda yang saya perasan masa pandemik COVID, we have this one hospital in Malaysia that is one kita panggil centralized place where we put all our COVID victims there, COVID patients. So bila kena COVID, dia tak ada sense of smell, sense of rasa pun tak ada. Jadi kadang-kadang makanan tu sudah basi tau ibu. Kerana dibagi pada this COVID patient. So dia selain daripada kena COVID, dia dah kena food poisoning pula. So saya pun rasa macam, oh my god, we need to have an action. So that kita boleh bantu orang ini tidak menambahkan lagi masalahnya lah.
Sudah dapat masalah lagi ya.
Ya betul, betul.
Kalau di Indonesia apa itu namanya? Sudah jatuh tertimpa tangga pula gitu.
Ya betul.
Yeah.
Sudah jatuh di timpa tangga ya ibu.
Yeah. Okay,
Okay.
maybe we can continue. Student, is there any question maybe from the student? We still have maybe around 10 minutes for Q&A session. Benedict, do you have any question? Maybe Marvel. Okay. There is still no
The
question.
student is a bit shy today. It's okay. It's okay. It's Friday afternoon. Everybody is tired, I guess. It's okay. I understand.
Yeah, they have a practical skill
I
class
see.
in the morning and then continue
And
with
the lecture in the afternoon. Yeah.
Okay.
I
Maybe I
understand.
will ask again, Dr. Nadiah. About OMF or oscillating magnetic field. Is it the same with pulse electric field or a different mechanism?
Oscillating magnetic field is not the same as pulse electric field. If oscillating magnetic field is a bit the same as radio frequency, ultrasonic even. Macam the caranya lebih kurang macam gitu juga. Tapi saya again, I'm sorry sebab saya pun tak berapa familiar juga dengan oscillating research. But the mechanism lebih kurang. Kalau ibu perasan kan, macam a lot of this technology banyak menggunakan electrode. So electrodes is the basis of it. But whatever the mechanism that is inside is depending on ultrasound or electromagnetic field, or depending on electrical itself, or even depending on the frequency. So depending on the source of it, it would result a different mechanism. So oscillating, I would assume lebih kurang sama macam ultrasound juga, but it's not the same as pulse. I'm sorry kalau saya salah ya ibu. Saya pun tak berapa familiar dengan that technology.
Okay, thank you, Dr. Nadiah, for the comment.
Yeah,
And I would like to highlight about the makanan tradisional yang di Kaleng, or maybe traditional canned food. Yeah.
Okay.
In Indonesia, we have many authentic cuisine and also traditional food, and small and medium enterprise want to market their product worldwide. So we have faced difficulties in what is it called, to redesign their package, and also how to test their heat penetration if we want to make in canned food. For example, maybe rendang, maybe in the form of canned food rendang, or maybe canned beef balado and other.
Betul.
Yeah. If I'm not mistaken, they have to pay 30 million rupiah if they want to test their product before they can market. Yeah. So it's very costly, and for small and medium enterprise, maybe they cannot afford. But how about in Malaysia? In Malaysia, small medium enterprise, they want maybe have the same trend, maybe want to change their packaging, and also how to
at the moment, kalau saya tengok trendnya di Malaysia, retort teknologi sekarang ni banyak digunakan, especially rendang tadi, balado saya tak ada dengar, tapi makanan macam rendang ayam, ada this what we call serunding ayam, serunding daging, this chicken floss, kan, beef floss. Dia banyak menggunakan retort processing. The best part about retort processing is that it uses pouches instead of canning process. Canning technology needs a very good technology to make sure that the sealing process of it is very good, and there is a bit of a complicated technology to be used by the SME. So in Malaysia, kita banyak gunakan aluminium pouch. So aluminium pouch tu is very flexible, and here we have what we call macam project community tau itu. Project community, jadinya dia kerajaan negeri akan beli satu retort teknologi, satu retort mesin, and then dia akan letak di project community. Project community ni siapa-siapa sahaja yang ada produk makanan, dia akan consult with kerajaan negeri on how to market their product. So dia akan pergi kepada this project community, dia orang akan test. So akan letak makanan dekat dalam aluminium pouch and then letak dalam retort processing tu. So selepas itu, untuk measure the temperature inside is very hard. So what they do is dia simpan makanannya di dalam room temperature. Meaning dia letak makanan dalam room temperature untuk lebih daripada 3 bulan. So jadi setiap minggu dia akan test produknya. Dia akan test in terms of taste, in terms of smell, in terms of the color. So kalau at a certain point makanan tu dah mula start ada bau yang agak lain, colornya pun sudah berubah ataupun teksturnya pun sudah berubah, then dia usually consider that is dia punya shelf life. So that is one of the techniques that we use here. So that it will not incur a lot of cost onto the SME producer. And it's a bit easier lah. Jadi kita pun boleh ajar mereka macam cara R&D yang paling mudah. Jadinya dia pun boleh akan bila nanti later on dia tak pergi kepada project community ni, dia boleh buat sendiri di rumah ataupun di tempat processing area mereka. So that is one of the initiative that was being done here. Tapi dia lebih banyak di kawasan-kawasan kampung. Di kawasan-kawasan bandar tak berapa sangat. Di kawasan bandar lebih bigger scale. Di kawasan kampung, the community focuses more on ibu-ibu tunggal, widow, balu. Jadi orang yang tidak punya suami lagi. Jadi untuk bagi diorang economic freedom and economic development in terms of untuk diri mereka dan keluarga mereka sendiri. So that is how we do it here lah. Tapi kadang-kadang ada jugalah isu-isunya. It doesn't go as smoothly lah. Kalau in Indonesia, I think because of the land area is much bigger, negaranya lebih besar kan daripada Malaysia sendiri. Jadi that's why kadang-kadang inisiatif macam ni lebih mudah dilakukan di kawasan yang kecil daripada kawasan yang besar. Sebab exposure-nya lebih banyak kan. Lebih cepat sampai. I hope I answer your question.
Yeah, thank you, Dr. Nadiah, for sharing the experience. Yeah, because especially in West Java, here we live in West Java, we have many traditional food, and every SMA want to market their products in maybe in kekinian, what does it call? Maybe kekinian. They want to transform their product into yang bisa disukai oleh
lebih industrial scale, lebih besar kan. Ya, saya faham. Tapi mahal juga ya, sampai 30 apa tadi
30
juta
juta.
ya, 30
Juta,
juta.
30 juta rupiah. And it takes around three months. 3
3
months
months,
for testing the heat penetration test, and then yeah.
But canning process, tak terfikir untuk guna pouch?
Maybe pouch or retort processing using pouch.
Using pouch is better.
Yeah, belum banyak
Belum banyak lagi.
dikeluarkan untuk SME, but for big company.
Saya rasa retort teknologi banyak dijual oleh industri dari China. Dan kadang-kadang kita boleh dapat harga yang agak murah daripada even Malaysia, producer banyak beli daripada China, daripada Malaysian producer sendiri. Kadang harganya a bit different kan.
Yeah. Okay. Yeah. Terima kasih Dr. Nadiah. Okay, maybe is there any question? Jika tidak, mungkin satu hal lagi Dr. Nadiah regarding food irradiation. Yeah. If I'm not mistaken, I ever heard about radiolysis. Radiolysis is a phenomena of what is called DNA lysis from the bacteria. So after bacteria contact with the gamma ray, they break the DNA. Okay. So it makes the bacteria inactive. So is it harmful for people or maybe for operator if we contact too much with radioactive, maybe gamma rays, radioactive maybe?
Betul.
Yeah, how about these issues?
That's why kalau kita tengok kan teknologi radiasi ni lebih regulated by government. Tak ada orang persendirian yang boleh buat teknologi atau menggunakan teknologi radioaktif pada industri mereka. Okay, kalau di Malaysia pun it is regulated by, kita panggil Malaysian Institute of Nuclear Technology. So that institute sahaja, kalau you sendiri sebagai fruit producer nak ekspor keluar, you have to come to MIN atau kita panggil tadi Malaysian Institute of Nuclear Technology untuk radioaktifkan you punya produk untuk hantar keluar. That is how we manage the safety part of it. Untuk pekerja dekat dalam tu, kalau saya tidak silap, mereka ada dipanggil giliran tau ibu. Dia tak boleh kerja hari-hari. Jadinya hari ini kalau dia sudah bekerja, lagi 2 hari baru dia akan kerja semula. Jadi ini dia nak kurangkan exposure gitu. And of course the safety gear has to be worn, and dia orang akan hantar untuk medical check up every year to make sure there's no effect from that. And dia satu lagi, in terms of the facility pun also kena bagus. Jadi macam saya mention tadi, kalau regulation by the United States, kalau dindingnya kena minimum 6 kaki. So untuk make sure safety is uphold. So kalau di MIN, itu yang saya dengar lah sampai setakat ini.
Okay. Terima kasih Dr. Nadiah. Maybe the time is up. Okay, please, do you have any closing statement?
Oh, okay. No closing statement, but well, I will see them in next 2 weeks, right? In the 9th of June, okay? In the 9th of June. So I think I've given you the presentation, right? I mean the slide for the assignment. Okay, so I hope you guys can form a group of 3 or 4 people and prepare a 15-minute presentation. It doesn't have to be very long, maybe just 5 slides, okay? And answering all those questions that I have. It's more of a discussion. I would like to see the advancement of Indonesia in terms of non-thermal technology, or maybe you have more ideas on how to change or to upgrade the technology of food processing in Indonesia. So pick one traditional product, macam Ibu Asri just mentioned. Take one traditional food product that you can change using the new non-thermal technology. Itu sahaja.
Okay.
Alright.
Right, terima kasih Dr. Nadiah. Maybe I want to remind again, here we already submit the assignment in live Unpad, regular live Unpad. Student, you can check whether we already upload the recording material, the last the first session, and we already put the assignment from Dr. Nadiah in the assignment here. Maybe you can check in live Unpad. Silahkan dibuat presentasi kelompoknya sesuai dengan kelompok praktikum. Due date-nya untuk disubmit link YouTube-nya itu tanggal 8 Juni, because 9 June every group will present their topic. Dan di sini sudah ada ya, sudah ada there are some questions here. Ini belum muncul. Oke, di sini ya di class presentation. Oke, sudah ini diabaikan, tanggalnya sudah direvisi 9 Juni. Jadi masing-masing kelompok akan memilih salah satu topik untuk non-thermal processing, dan silahkan dijawab pertanyaan dari Dr. Nadiah ini ya. Jadi sistemnya adalah Anda merecord dulu presentasinya, tadi kurang lebih minimum 5 slide gitu ya, kemudian nanti akan dipresentasikan dan didiskusikan di minggu depan. Seperti itu ya, jadi silahkan cek di live Unpad. Oke, thank you, maybe itu tambahannya. Baik, sebelum kita akhiri, terima kasih sekali lagi untuk Dr. Nadiah atas presentasinya yang sangat menarik dan memberikan very meaningful for us here, and thank you for the insight. Maybe students, could you please turn on your camera? We will take screenshot. Please, bisa dibuka kameranya untuk screenshot, dan kita bisa segera mengakhiri kelas hari. Oke, kok jadi tinggal sedikit ya. Where others? Tinggal 11 nih, tinggal sedikit. Okay, maybe there are some students have operational research class, so they keluar dari Zoom ini. Oke, kita hitung. Silahkan Nur mungkin bisa di open cam-nya. Oke, kita hitung ya. Oke, 1, 2, sebentar. Oke, one more time. Terima kasih sudah. Thank you again, Dr. Nadiah, for joining with us during this emerging thermal and non-thermal lecture today. I hope we can see again maybe in next 9 June. Yeah,
9 June. All right. Thank you, everyone. Take care. Jumpa lagi.
Ya, terima kasih Ibu. Thank you for wonderful participant student. Ya.
Okay. Jumpa lagi ya Ibu. Lagi 2 minggu.
Terima kasih.
Terima kasih.
Yes.
Saya lead group ya.